Okay, good morning, gang. So I have some news that you'll all be happy to hear. First, I should go close my door. But then I have news that you'll all be happy to hear. Kimmy, you gonna stay here with me, okay, this one? No more series. No more series of any sort. No more power series, no more nothing. You won't see another capital Sigma outside of exam 3 and the final for the remainder of the course. Congratulations, you made it. That said, if there are any problems from the homework that closed today, any problems from homework 11 or any of the other serious stuff that you guys are being irritated by, haven't been able to finish or whatever, I would be happy to take a look at those because today we don't have a whole lot of new material to drop. I am going to show you some new stuff. We're going to be moving to chapter 8. But before we do that, I would be happy to take a look at one or two homework problems. So this, of course, is MAC2312, section 002, lecture 11, 18, 20. I've spent the last couple days going back through the grade book and getting every little old thing put in. So all of your study guide grades should be in, all of your exam grades should be in. If there's anything that you handed in late or weird or couldn't submit this part of it on Canvas, so you sent that part of it to me through email, all that stuff should be in. Do me and yourself a favor and take a look now, or at least sometime this week, and make sure that there isn't anything that you've handed in and not gotten credit for. I've had a few people say, oh, part of the study guide file submitted, so you gave me like, 20 out of 25, but I did the rest of them. They're here. They just didn't like go through on Canvas, shit like that. So make sure that everything is as it should be in the gradebook, because the gradebook should now be 100% up to date. Like I said, today we're going to talk about section 8.1. We're going to begin the applications with section 8.1, which is on Arclength. But first, I would like to look at any series problems that you guys would like to look at. So is there anything from homework 11 that you guys would like to look at? If so, please let me know in the chat there. Number 10 from homework 11 and 16. Okay, I think that's a good start. 10, 16, and 20. So let's look at number 10. Okay. So this homework came due today. We had extended it to today. If you do need more time on it, please just submit an extension request. I'll be going through and clearing those today. They say find the Taylor series centered at 8. If the nth derivative, fn of 8, so that's the nth derivative of f, evaluated at x equals 8, is negative 1 to the n times n factorial over 6 to the n times n plus 5. All right, so we're going to start here. The Taylor series centered at 8 for f of x. This is f of x equals sigma n from 0 to infinity, fn of the center, which is fn of 8 over n factorial times x minus 8 to the n. And this piece is the thing they gave you. So that's sigma n from 0 to infinity, negative 1 to the n, n factorial over 6 to the n times n plus 5, all divided by n factorial times x minus 8 to the n. So one of the things that folks sometimes have a hard time remembering is that whatever goes here, the center of your series, which they told us centered at 8, is what you plug into the nth derivative when you go to find your CNs. So what they gave you, fn of 8, the nth derivative of f evaluated at x equals 8, is exactly the hard piece from your Taylor series table. So we just plug in here the thing they gave us. And now we should simplify a little bit, really. This is -1 to the n factorial over 6 to the n plus 5 times 1 over n factorial, excuse me, times x minus 8 to the n, and you can cancel the n factorials. Oh, -1 to the n over 6 to the n times n plus 5 times x minus 8 to the n. That would be your final answer here. And if you want to find the interval and radius of convergence, you would run the ratio test. Do we want to see the IOC work? Who requested this? Where did my chocolate go? Matthew, did we want to see the IOC work here? Okay. So they want they actually asked for the radius of convergence. But we get that all out of the ratio test. So remember, L from the ratio test is always the limit as n goes to infinity, absolute value an plus 1 over an, which here is going to be the limit as n goes to infinity, absolute value of, here's an, so an plus 1 is -1 to the n plus 1, x minus 8 to the n plus 1 over 6 to the n plus 1 times n plus 6, right? N plus 1 plus 5 is n plus 6. And now we'll multiply by the reciprocal of an, that's 6 to the n, n plus 5 over -1 to the n, x minus 8 to the n. So this object on the left is our ratio test limit that I get by plugging this an in here. This is an plus 1, and here I'm multiplying by the reciprocal of an. That's how we can divide by an. Now I group the terms. So I've got -1 to the n plus 1 over -1 to the n times x minus 8 to the n plus 1 over x minus 8 to the n times 6 to the n over 6 to the n plus 1. Is that everything? Oh no, the n plus 5 over n plus 6. All right. So since I've got two fractions here and everything in those fractions is being multiplied, I can do that in whatever order I like. So I shuffle the similar things together. And then I would split up the absolute values. So this is lim n to infinity, and I can simplify a little bit. -1 to the n plus 1 divided by -1 to the n, that's just -1. X minus 8 to the n plus 1 divided by x minus 8 to the n is just x minus 8. 6 to the n divided by 6 to the n plus 1 is 1/6. So no calculus there. I haven't taken any limits. I'm just doing algebra. And then I still have this n plus 5 over n plus 6 piece here. And I can give the absolute value to each of these pieces on their own. Again, because they're all being multiplied. Absolute value is a multiplicative function. The absolute value of -1 is 1. The absolute value of 1/6 is 1/6. And the absolute value of x minus 8 is x minus 8. So I'll have lim n to infinity, absolute value of x minus 8 times 1/6 times n plus 5 over n plus 6 is positive, so I can ignore the absolute values there. And this piece goes to 1 as n goes to infinity. You can renormalize if you want, or you could use L'Hopital's rule. So what we get out of this is absolute value of x minus 8 times 1/6. That's L. So L is less than 1 if and only if the absolute value of x minus 8 times 1/6 is less than 1, which is true if and only if the absolute value of x minus 8 is less than 6. I'm just multiplying both sides by 6 to get rid of the 1/6. And then I can unpack that as -6 is less than x minus 8 is less than +6. And then finally, I can add 8 everywhere, and this will give me the open version of my interval of convergence. -6 plus 8 is 2. X minus 8 plus 8 is x, and 6 plus 8 is 14. So the IOC is 1 of 2 to 14 open, 2 to 14 left closed right open, 2 to 14 left open right closed, or 2 to 14 closed on both sides. All of which have radius 6. So your center is here. I'm sorry, your center is 8. So if you come down to 2 and up to 14, this distance is 6. Sorry, this looks sloppy, doesn't it? This is an 8. So the interval of convergence is one of these guys. I don't know whether or not to include endpoints until we go back and test the two endpoints. You can plug in x equals 2, see if you get a convergent series. Plug in x equals 14, see if you get a convergent series. And that would tell you which of these 4 to pick. But they all have the same radius. They're all centered at 8. So the distance from the center to an endpoint, that's your radius, remember, and that distance is 6. We could, in fact, stop here and say, this has to be my radius of convergence. If you think about, go way back to like college algebra when you learned about absolute value inequalities for the first time, one way to read this is all numbers x whose distance from 8 is less than 6. That means you're centered at 8 and you're not allowed to walk further than 6 units away. Oh, that means that this 6 has to be your radius of convergence. But this is the normal procedure, right? After you get here, you write down the possible IOCs. And then if you wanted the exact IOC, you would have to plug in 2, see if that series converges, plug in 14, see if that series converges, and then select one of these. But since they didn't ask for the IOC, they just asked for the radius. You can draw the picture and see that the radius is 6, or you can kind of think about it from here. Questions on this? I think my chat is acting up a little bit. I'll ask you to be patient with me. For some reason, it's not showing the notifications. Yeah, okay. Questions on this?
I have a question.
Yeah.
Not so much about the problem, but during the homework, we had to use a ratio test for like a lot of the problems.
Yep.
And is that like a fair question for like, would this be like a fair question for like exam 3, considering the ratio test is from exam 2?
Oh, yeah.
Like a tool we're gonna use for the rest of the, like for test 3?
Yes, I could ask you to do this on exam 3, right? This is a power series thing. Exam 3 includes power series, right? So exam 2 is sections 7.8 through 11.7, and then exam 3 picks up there at 11.8, 11.8, 11.9, 11.10. All of those sections involve heavy use of the ratio test. So just because you first saw it on exam 2 doesn't mean you couldn't also see it on exam 3. Definitely the current homework has a lot of ratio test work, and you could expect exam 3 to have a meaningful amount of ratio test work. Every time you need to find an IOC for a power series, you'll be using the ratio test.
Would that apply to the other test too?
Which other, the final?
No, the like the other test, like anything from the
Oh,
test
yeah,
two.
well, yeah. So every time when you get here and you start testing the endpoints, you'll need some other convergence test, right? Like if I were to plug in x equals 2 here, then I would get -6 to the n times -1 to the n over 6 to the n times n plus 5. The convergence test you would need to figure that out is going to be one of the other convergence tests. So yes, yeah, all of the convergence test stuff is still relevant for power series. It's just not the main focus. So in the same way that, exam 1 was not about testing your differentiation skills, you still needed to differentiate when you wanted to make a U substitution, right? So you still needed to be able to differentiate to do exam 1 in this class, which is all about integration. In the same way, to do exam 3 in this class, you will still need to use those convergence tests. They're now just a small part of a larger problem whose focus is something else.
Okay, thanks.
No problem. Other questions on this stuff? If not, I'm going to move on. We wanted to see 10, 16, and 20. So that was number 10. We can take a look at 16 next. Last call for questions on this. Okay, 16 then. Where did that go? I guess it went away. All right, 16, did I close it? Oh, that's cop one. God damn it. All right. Oh, yeah. 16 wants you to find a Taylor series for sine centered at pi. Okay, so you should attack this the same way we did finding the Taylor series for sine centered at 0. The only difference here is that we're moving the center from 0 to pi. So you need to make your table n, fn of x, fn of the center, which is pi, and then your cn's. When n is 0, if I differentiate 0 times, then my function is just sine of x. And when I plug in pi, sine of pi is 0. So C0 is 0. If I differentiate once, I get cos of x. The cos of pi is -1. So C1, C0 was 0. C1 is -1. If I differentiate twice, that's negative sine of x. The negative sine of pi is -0 is still 0. So C2 is 0. And you start to see the same sort of pattern emerge that we did when we first calculated the Taylor series for sine. This is still an odd function, so I still expect all the even terms to be 0. But something will be a little bit different compared to the series that's centered at 0 compared to the Maclaurin series. If I differentiate this again, the derivative negative sine x is negative cos x. Negative cos of pi is -1 is +1. So C3 is 1 over 3 factorial. When n is 4, the derivative of negative cos x is positive sine x. The sine of pi is 0. So C4, as we expect, is 0. When n is 5, the derivative of sine is cos. Cos of pi is negative 1. So C5 is negative 1 over 5 factorial. So we see a similar pattern as we did when we found the Maclaurin series for sine. And the nice way to get that into the sigma notation, you remember, was just to write it out. Remember here, though, that your series is centered not at 0, but at pi. So your series is going to look like sigma n from 0 to infinity, Cn times x minus pi to the n, which is C0 plus C1 times x minus pi plus C2 times x minus pi squared plus C3 times x minus pi cubed plus C4 times x minus pi to the 4 plus C5 times x minus pi to the 5, and so on. And now we plug in for these C's. C0 was 0. C1 was negative 1, so this is minus x minus pi, plus C2 was 0. C3 was plus 1 over 3 factorial, so that's plus 1 over 3 factorial times x minus pi cubed. Plus C4 was 0. C5 was negative 1 over 5 factorial, so that's negative 1 over 5 factorial times x minus pi to the 5. And if we don't write the zeros, then this is negative x minus pi plus 1 over 3 factorial times x minus pi cubed minus 1 over 5 factorial times x minus pi to the 5. What would my next term look like? What's the next non-zero term of this Taylor series?
1 over 7 factorial times x minus pi to the 7th.
Excellent. And then the one after that would be minus 1 9 factorial x minus pi to the 9, and so on. So again, it's an alternating series, just like the regular sine series. Again, all the even terms are 0, just like the regular sine series. There's one small difference. The Taylor series for sine, or the Maclaurin series for sine, centered at 0, has first term positive, second term negative, third term positive, fourth term negative. This one's flashing back and forth from positive to negative, but it starts negative rather than starting positive. But other than that, it looks very, very similar to the Maclaurin series. So if I want to write this as a sum from n equals 0 to infinity, I will definitely have my x minus pi to the 2n plus 1. I definitely have a 2n plus 1 factorial downstairs, the factorial of the odd numbers. And upstairs here, rather than a negative 1 to the n, which with the series starting at 0 would be first term positive, I'll have a negative 1 to the n plus 1. So this is all very, very similar to the Maclaurin series, just a little bit different. Questions on this one? I think it might be illustrative to look at the first few partial sums of this and compare that to the first few partial sums of the Maclaurin series. So let me clear some of these out. So here's sine x. Here's the first few terms of the Maclaurin series for sine x. So blue is sine, green is the T9, the Taylor polynomial of order 9, centered at 0. And let's do the same thing, but with the series we just found. That's negative x minus pi plus 1 over 3 factorial times x minus pi to the 3 minus 1 over 5 factorial times x minus pi to the 5 plus 1 over 7 factorial times x minus pi to the 7 minus 1 over 9 factorial times x minus pi to the 9. All right. Here's Maclaurin and sine. Here's the Taylor series and sine. Let me do this in a different color here. Let's do this in orange. So this one is centered at pi. This one is centered at 0. So if I wanted to approximate the integral of sine x from like 0 to 2, I could use this green polynomial, because from 0 to 2, the green polynomial is indistinguishable from the blue function. But if I wanted to integrate from like 3 to 5 or 3 to 6, the green polynomial would be a bad choice because it doesn't stay close to the blue function. This would be a better choice because from like 3 to 6, the orange function stays close. The center for the orange function is pi. And you can see the orange polynomial, it's kind of glued to the original function here at pi and is getting closer on an interval that's symmetric about that. The center for the first series is 0, 0. That's green, right? And you can see how the green function, the green polynomial, is sort of glued to sine starting or on an interval that is symmetric about its center. Okay, so both of these are order 9 approximations, or T9s. This first one is centered at 0, and the one we're looking at now is centered at pi. They do the same thing, they're just centered at different places. So the interval of convergence kind of grows out from that center. And if I wanted to do some work with the sine function close to x equals pi, the orange would be a better approximation to use. If I wanted to do some work with the sine function close to x equals 0, then the green polynomial would be a better polynomial to use. You guys feel like you see the difference between the two different centers? Centered at 0. Green stays really close to the blue as long as you stay close to 0. Centered at pi. The orange stays close to the blue as long as you stay close to its center, which is pi. And the convergence kind of grows symmetrically from this center. It's neat. All right, so that's that. If you want to find your interval of convergence here, same sort of thing as we did in the last one, ratio test it. If you only care about the radius of convergence, again, ratio test it, and then think about the possible intervals of convergence. So that was 10 and 16. The last one we wanted to look at was number 20. Yeah, okay, this is fun. So here you get to use your estimation theorem on alternating series again, believe it or not, because we want to approximate 1 over the 10th root of e. I'll write this down. Accurate to how many decimal places? 5. All right. So if we're going to be accurate to 5 decimal places, that means I need the error to be how small? Well, I couldn't have an error of 0.1. That would mean I could be off by 1 in the first decimal place. So it's got to be 0.0 something. Couldn't be 0.01 because then I could be off by 1 in the second decimal place. Can't be off in the third, fourth, or fifth, right? So 1, 2, 3, 4, 5. I need all of those to be correct. And then because I want to minimize the chance of getting a rounding issue, I'll just do this. So it says the error in the first 5 decimal places has to be 0, and then an acceptable error in the 6th decimal place would be 1. So the first 5 would agree, but then the 6th might be off by 1. You could get away with this being a 5, honestly, but because so many computer programs like to round, by making this a 1, you're reducing the chance that a rounding error will give you any trouble. This is a little bit of overkill, but since these first 5 are 0, you're guaranteeing that the first 5 decimal places will be correct. All right, let's tuck that in our pockets. We'll use it again at the end. 1 over the 10th root of e. How the hell could I possibly use a series to approximate this? Well, that's e raised to some power, right? That's e raised to the power of negative 1 over 10, right? Like e to the 1/2 is the square root of e to the 1/3 is the cube root of e to the 1/10 is the 10th root of e. I don't want that. I want 1 over that. So e to the negative 1 is 1 over e to the negative 2 is 1 over e squared. E to the negative 1/10 is 1 over e to the 1/10, which is 1 over the 10th root of e. So we'll use the fact that e to the x is sigma n from 0 to infinity 1 over n factorial times x to the n. Remember whose IOC is negative infinity to infinity. So you can plug anything from here into here and get a true statement. In particular, it's okay to plug negative 1/10. All right, so do we understand the strategy? The number I want to approximate can be written as e to the negative 1/10. I know that the function e to the x can be written as this series, and that you can plug whatever x values you want in because the IOC is negative infinity to infinity. So if I plug negative 1/10 in for x in this series, I will get e to the negative 1/10, which is the number I want. So e to the negative 1/10 should be sigma n from 0 to infinity 1 over n factorial times negative 1/10 to the n. And I want to clean this up as much as I can. That's sigma n from 0 to infinity. I have my n factorial downstairs, and then negative 1/10 to the n is negative 1 to the n over 10 to the n. So this series, which is now just a regular numerical series, right, no variables, converges because the IOC is negative infinity to infinity, and I plugged a number from that interval in. This series converges to this number. And the question is, how many terms of this series do I need to use to get this accuracy? Questions so far? All right. Lucky for us, this is an alternating series. So we can use our estimation theorem for alternating series. There is a separate estimation theorem for Taylor series in general. It's discussed in your textbook, and if you use the guide in WebAssign, it may reference you to this thing. I'll show it to you really quickly. But I don't hold you responsible for that in this class. In the non-honors versions of Calc 2, I do not hold you responsible for Taylor's inequality, which is discussed here. So this is kind of like your error or your remainder term, and it gives you a way to bound the error above. In terms of the n plus first derivative, it's not impossible to work with, but I found that it doesn't really sink in well. You guys have enough to worry about already, and we have an estimation theorem that we can use already. But if you do find yourself clicking through the master it, like help me solve this type things in WebAssign, you may see a reference to this. I advise you to stay away from this because I will not be testing you on it. But you are still responsible for the estimation theorem that we learned back here. All right, which looks very similar. It's just a lot easier to use. It's much simpler. It says that the error, Rn, the thing that we want to make small, is always less than Bn plus 1. So this says that we need to solve Bn plus 1 is less than 0.000001. And here, Bn is the non-alternating part of this summand. It's 1 over n factorial times 10 to the n. So our inequality is 1 over n plus 1 factorial times 10 to the n plus 1 is less than, this is 10 to the negative 6, so just I'll write it as 0.000001. And the easiest way to solve this inequality is just guessing and checking. There's no convenient way to undo the factorial here that you would need to solve. So I'll just plug in a few values for n and try to get a feel. If we think n equals 2 might do the job, then that's going to be 1 over 3 factorial times 10 to the 3. And 3 factorial is 6, 10 to the 3 is 0.001. So this is 0. I'll just use decimals here real quick. So 1 over 10 to the 3 times 3 factorial. This is 0.0001. And then 6 is 666, blah, blah, blah. So this is not yet small enough, right? I want this thing to be less than 0.000001. When n is 2, this thing is 0.0001666666. So we got to go further. We'll try n equals 3. Then I'm looking at 1 over 4 factorial times 10 to the 4. So if I swap these 3's for 4's, 10 to the 4 factorial. That's getting there. That's 0.000004. 1 and then 6 is 666. Blah, blah, blah. Still not quite there. Got 5 zeros and a 4, 5 zeros and a 1. So we go 1 more to n equals 4. And that's going to be 1 over 5 factorial times 10 to the 5. And this will certainly be small enough. Let's see what we actually get just for fun. Yeah, 8.3 times 10 to the negative 8. That's 0.0000000. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So this would be 8, 3, 3, 3, and so on. All right. So the first value of capital N that solves this inequality is 4. When capital N is 3, we're not quite there. We're really close. When capital N is 4, we are way smaller. So N equals 4 works. E to the negative 1/10, the thing I want is approximately sigma little n from 0 to 4, negative 1 to the n over n factorial times 10 to the n. Which is, let's see, when n is 0, this is 1, and then minus 1 over 10, 1 factorial times 10, and then it would be plus 1 over 2 factorial times 10 squared, and minus 1 over 3 factorial times 10 cubed, and plus 1 over 4 factorial. All right, and I know that this will have the desired accuracy from my theorem and the work I just did. And I can ask Wolfram Alpha or something like that to do the computation, or you could feed this to your calculator if you wanted. I'll do it the quicker way. We're going to sum negative 1 to the n over n factorial times 10 to the n from n equals 0 to n equals 4. And here it is. This is 72,387, 72387 divided by 80,000, which as a decimal is, here it is, 0.904 8375. Okay. So the n equals 4 partial sum does the job. Oh, shit, sorry, I'm getting something important on my phone. And we can compare this to the actual value of the series, which is e to the negative 1/10. If I calculate e to the negative 1/10 in Wolfram, I get this decimal, 0.9048374. So the actual value (0.904837418 blah blah blah). And we can see if we got the first 5 decimals right. So I scribbled the actual value up here where I had room. Decimals are 904837418, the first 5 of which 90483, 90483. Yeah, we nailed it. Not only that, we got the 6th decimal place correct also, and we're off in the 7th decimal place by only 1. So this is a very good approximation for this number. And we were able to cook it up using what we know about power series, and even able to verify its accuracy via the estimation theorem for alternating series. I would expect something like this to show up in at least one of exam 3 or the final. And I'll just tell you. On exam 2, the estimation theorem problem did not go well. A handful of people did manage it very well, both parts. But for the most part, there was at least one little mistake in everybody's work. So I want you to spend the time between now and exam 3, making sure you're really comfortable with those theorems. Definitely read the comments that I left in your exams. All right, so those were the homework problems we wanted to take a look at. Now for the actual material of today, I promise we're out of series land. We're done with series. So I'm not dumping any new information having to do with series on you. Instead, we're going to start talking about arc length. Homework 11 did close today, but if you weren't able to finish it, if you need more time, as always, please submit an extension request. I'll go through and grant them. The arc length problem says this. If I give you some curve and an interval from like A to B, and you think of this curve as like a rope, what is the length of that curve? So we know that it's not the same as the straight line distance, right? Can we find the length? And in this case, it's going to be defined by the graph of a function. So like pretend that this portion of the graph is a piece of rope. If you're able to like stretch that rope tight, how long would it be? Turns out to be a bit of a tricky question, and it's one that we're going to answer using an integral. The integral that we cook up comes from something very similar to a Riemann sum. In general, these problems are hard. The reason we do them after sequences in series is because in real life, or if I wanted to punish you, most of these integrals are hard enough that the best way to do them is to do them as a series. So you write the inside as a series and then integrate that series instead. In practice, I won't do that to you. I don't want to abuse you guys any more than is absolutely necessary. And I feel like you've had enough of the infinite series abuse at this point. Another way of thinking about this is if I was a little dude walking along this graph, how far would I have to walk to get from the point over here, which is a comma f of a, to the point over here? Remember, since this graph is y equals f of x, the y value up here is f of a, and the y value here is f of b. In order to answer this, I'm going to go through the derivation of the arc length formula. The arc length formula, I'll show it to you right now, is the integral from a to b of the square root of f primed squared plus 1. So you can see that even if this was a really simple function, even if you're just dealing with the function f of x equals x, or f of x equals x squared, f of x equals x would be trivial, but f of x equals x squared would be a little bit complicated. You would need some trig sub. This kind of already looks trig subby. Here's the trick. And we're going to need to go through this very similar thing to this again when we talk about parametric curves. So I'd like you to pay attention, take good notes here. exaggerate the curvature a little bit, call this A, and call this B. Partition the interval AB into n equal length subintervals, each of width delta x, just like in Calc 1, b minus a over n. So I take this interval and I chop it up. I'm going to chop it into a specific number of intervals here. So a would be x0, and then this would be x1, x2, x3, x4, x5, and b here would be x6. And each of these widths is the same. They're all delta x. But now I'm not looking for area. So I'm not going to come in here and place some rectangles. Instead, I'm going to come up here to each of these points that's on the graph above these guys. And I'm going to approximate the length of the curve along each subinterval with a straight line. So this first guy, I say, I don't know exactly what the length of this curve is, but it should be pretty close to the length of this straight line connecting those points. I don't know exactly what the length of this piece is, but it should be pretty close to that. This should be pretty close to that, and so on. So on each subinterval, we approximate using straight line segments. Okay.
Sorry, is that XC there? X sub C? Is that what that says?
No, x6.
6, okay.
Yeah, x0, x1, x2, x3, x4, x5, x6. So this point right here is x1 comma f of x1. And this point right here is x2 comma f of x2. And I'm going to look at a little right triangle. The width here is the distance between x1 and x2. That's delta x. And that would be the same for any of these. All of these have the same horizontal distance, delta x. The height here, though, changes. It depends on which little line segment you're looking at. I would call this guy delta y2, because it is the height of the second little subintervals triangle. And then I can use the Pythagorean theorem to figure out the length of that line. And the same rule works for all of these. The straight line distance from, we'll think of this as like P0, this point I would call P1, this point I would call P2, this would be P3, P4, P5, and P6. The straight line distance from Pi minus 1 to Pi will denote that by bar pi minus 1 pi. So like this is P0, P1, this is P1, P2, this is P2, P3, this is P3, P4, this is P4, P5, and this length here would be P5, P6. By the Pythagorean theorem, this is the square root of delta yi squared plus delta x squared, right? Yeah, squared. A squared plus b squared equals c squared. If you look here, this little length is P1 to P2, yeah, P1 to P2. And according to Pythagoras, that thing squared should be delta y2 squared plus delta x squared. So take square roots. And that same recipe works, not just for the length of the second one, but for all of these, for the length of the first, second, third, fourth, fifth. In general, the distance from one of these points to the next point is the square root of the change in y squared plus the change in x squared. I could put a little right triangle for each of these things and use the Pythagorean theorem on each. So to approximate the total length, I need to add all these up. I'm going to switch back to black here because I know the pink is a little hard to read. So the total length is approximately the distance from P0 to P1 plus the distance from P1 to P2 plus the distance from P2 to P3 all the way out to the last one, which would be the distance from Pn minus 1 to Pn. So I add up all the little lengths, all the little pink lengths. I think if you look at all these little pink lengths, we would agree that if you add up all these little straight line lengths, that's pretty close to the length of the curve here. And the more of these little line segments I use, the better it will get. So we're going to send n to infinity eventually. But for now, I just want to get a formula for this. This is the sum from I equals 1 to n, length pi minus 1 to pi. And the length from pi minus 1 to pi, right, if you try plugging this in, when I is 1, this is p0 to p1. When I is 2, this is p1 to p2. When I is 3, this is p2 to p3, and so on. So you add those up, you get this. And then we have a formula for the length from pi minus 1 to pi. So this is sum from 1 to n, square root of delta yi squared plus delta x squared. And from here, I do some sneaky algebra. Now I can force factor delta x squared under the radical. What do I mean by that? Well, I mean, I'll have sigma I from 1 to n, square root of, yeah, I mean, relax, Papa, it's okay. Delta yi squared over delta x squared plus 1 times delta x squared. And this is the same as sigma I from 1 to n square root of delta yi over delta x squared plus 1 times, now outside the square root, delta x. And this looks like a Riemann sum. As n goes to infinity, the following things happen. Delta yi over delta x goes to dy dx, which is f primed of x. And delta x goes to dx. So this total length is approximately this. And as n goes to infinity, the other thing that happens is the approximate becomes exact. Right? If I were to use infinitely many of those little pink segments, then I would get the actual area. The more and more of those segments I use, more and more shorter and shorter segments, the more accurate this approximation becomes. So as n goes to infinity, I get that the total length is exactly the integral that this Riemann sum becomes, which is the integral from a to b square root of, this is going to become f primed, so this is going to be f primed of x squared plus 1 dx, which is the formula that I gave you at the start. So that's it. That's the proof, or that's the derivation of this formula. And really, that's it. So now we just need to get a little bit of practice with this formula. Unfortunately, this does sort of come down to one of those memory things. You must remember this formula. There are going to be some other formulas like this that you will have to remember, but it's not going to kill you. It's not a terribly hard formula. And later, when we get to parametric curves, I'll give you another formula for arc length that is a little more intuitive. Okay, so this is the length of the curve y equals f of x from x equals a to x equals b. We got to remember this. Of course, for this to work, f needs to be differentiable so that f primed exists. But that's okay. That's not a terribly rough restriction. Most of the functions we play with are differentiable. I'll grab an example from your textbook. And you'll see here the same picture that I showed you. And they say the exact length is the limit as n goes to infinity of the sum of the short lengths. They use the distance formula, and they get the same formula we did. So they want us to semi-cubal parabola. So they want us to find the length of y equals x to the 3/2 from x equals 1 to x equals 4. All right. The picture y equals x to the 3/2, they have it here. I'm not crazy about that picture. Let me show you something a little clearer. All right, here's what we're working with. And we want to find the length from x equals 1 to 4. So we're looking for this length, the length of this curve. It's not a straight line, but now we can do it. So f of x here is x to the 3/2. A is 1 and b is 4. So my arc length formula requires the derivative here. So I'll calculate f primed. That's 3/2 x to the 3/2 minus 1 is 1/2. So f primed all squared is 9/4. X to the 1/2 squared is just x. So the length, which traditionally in differential geometry we would call S, but your book uses L. I'm going to avoid any confusing notation just by writing length, is the integral from A to B of the square root of f primed of x all squared plus 1 dx, which is the integral from 1 to 4, square root, f primed was this, f prime squared was this, so this is 9/4 x plus 1 dx. Who can help me with this integral? It's been a while since we've had to do any challenging integrals. How do we do this? Is this a hard integral?
No, we can just substitute 9/4 x plus 1 for z, just do u sub.
Excellent. Yeah, I can sub for the whole radicand. So I'll let z be 9/4 x plus 1. Then dz is just going to be 9/4 dx. I do need to change my bounds. When x is equal to 1, z will be equal to 9/4 times 1 plus 1, which is 9/4 plus 4/4. 9 plus 4 is 13, so that's 13/4. And when x is equal to 4, z will be 9/4 times 4, which is 9, plus 1 is 10. So here's all the stuff I need for my substitution. And this integral will become the integral from 13/4 to 10, square root of z times dx, which is 4/9 dz, right? If you divide both sides by this. And you can pop out the 4/9, rewrite the square root as a power. So this is 4/9 integral from 13/4 to 10 z to the 1/2 dz, which is now a power rule integral. I'll add 1 to that power and divide by that new power. So I get 4/9 times, I'll have z to the 1/2 plus 1 is 3/2, and then I need to divide by 3/2, so that's multiplying by 2/3. And I have to evaluate this whole apparatus from 13/4 to 10. You can combine these two constants. 4 times 2 is 8, 9 times 3 is 27. So that's 8/27 times 10 to the 3/2 minus 13/4 to the 3/2. Neither of which are nice numbers, so I wouldn't bother simplifying beyond this. This is fine. You're okay, buddy. You're okay. All right, any questions on the calculation here? Sure, Bob. Sure. So this is an example of a nice problem. These problems can get out of control quickly. If you're all comfy with this, I'd like to show you a less nice one. So let's find an integral representing the length of y equals 1 over x from x equals 1 to x equals 2. The picture here is not hard to imagine. 1 over x. It's like this. So here's 1 comma 1. And here's 2 comma 1/2. I'm looking just for this length. So f of x here is 1 over x. A is 1 and b is 2. F prime of x, the derivative of 1 over x is negative 1 over x squared. Right, negative 1 times x to the negative 2. So f prime squared is negative 1 over x squared all squared. That's positive 1 over x to the 4. So this exact length would be the integral from 1 to 2 of the square root of f prime squared plus 1 dx, which is the integral from 1 to 2 of the square root of 1 over x to the 4 plus 1 dx. And this doesn't look like a hugely intimidating integral. I mean, it's not as scary looking as some of the things I asked you guys to do leading up to exam 1. But in that way that integrals can be a little bit deceptive, this is actually very hard. So you could stop here. We found the integral representing the length. It's this. Can we try to evaluate? Well, I could combine into a common denominator, and I'd have integral 1 to 2, 1 plus x to the 4 over x to the 4, all under my square root. And then I can take the square root of the top and bottom separately, so I'll have 1 plus x to the 4 under a radical upstairs. And downstairs here, I'll have x squared. Now I can't treat this as 1 plus x squared, right? Square roots do not fuck with addition at all. This does not split up. From here, this kind of looks trig subby. Right, if this was an x squared, I know that the square root of 1 plus x squared, I would normally handle with the substitution x equals tan theta. So maybe I think of it as integral 1 to 2, 1 plus x squared squared under the radical, all divided by x squared dx, and try the substitution x squared equals tangent theta. That's not a crazy idea. But then your differential is 2x dx equals secant squared theta d theta. And I don't have an x dx upstairs to play with. So this is trouble. In fact, it's such bad trouble that we're not going to be able to do it. I haven't played with this particular integral a whole lot, but I do have an awful lot of experience with integrals in general. And I can tell you that the fastest way to solve this integral would actually be to come back here, rewrite this thing as a power series, which means lots of work with Taylor's formula, and then integrate that infinite series. Not a pleasant process. Not a pleasant process at all. So this is where we are. These arc-length integrals are tough. The reason I said find an integral representing the arc length rather than find the length is because you can't solve this integral. As relatively innocent looking as this integral is, there's no closed form antiderivative for this function. You're not going to be able to use FTC2 to evaluate this in the way that we normally would, where you find an antiderivative and then plug in the bounds, because there's no nice antiderivative here. Just like sine x over x has no nice antiderivative. We only saw that integral when we did it as a series. The textbook has a number of problems like this. I think they do some part of this one that I just did. Here it is, yeah. And they use Simpson's rule, which is an approximate integration technique. It's a Riemann sum. It's a finite Riemann sum. They do it with n equals 10 to get a reasonably good approximation, but it's not exact. And in general, it's very, very hard. The last thing I want to talk about, oh no, we're out of time today. Okay, so this is where we're going to stop for today. You can define a function to be the arc length of some other function from a up to x. And this process is called parametrization. You can reparametrize a function by its arc length, although I don't think they ever do it here. It's one of the things that in differential geometry, if you're ever to go on to study general relativity or any particular bits of interesting space-time geometry, reparametrization by arc length is a common thing. I won't be making you do that, although I may ask you to calculate the arc length function itself. Next time, we're going to talk about surface areas. So this is going to be a lot like the volume problems we did at the beginning of the semester, only instead of finding volume, you're finding surface areas. The way we do that is by taking a little section of arc length and rotating that little section of arc length to get a little section of surface area. Then you'll integrate that little section of surface area. So the integrals we'll be doing here will have the little arc length component, but then it will also have something else, and you'll have to do those integrals. Sometimes this actually makes these easier. And then we're going to move to chapter 10. We're going to do these same things, but in the setting of parametric curves. We will talk about finding arc lengths and finding areas and tangents and stuff for parametric curves. And then we're going to talk about polar coordinates. Polar coordinates is something you should have seen in trig pre-calc, but maybe you didn't see in enough detail. And of course, we're going to finish the show here by learning how to do calculus in polar coordinates. So again, finding areas and tangents, that sort of thing. And that's the end of the class, lads and ladies. That's it. That's where this class ends. This class ends in section 10.4, doing calculus with polar coordinates. It's going to move pretty quick from here to the end. It may not feel like it, but you're almost to the very end. So today is the 18th. Next week is Thanksgiving. And then the week after that is the last week of school. So I'm going to open up one more homework for you guys this week. It's just going to have 8.1 and 8.2 stuff. I'll make it a short homework and I'll have that be due on Monday.
What?
So I'm going to open up a homework for you today. It will have 8.1 and 8.2 stuff.
Mm-hmm.
That will be a short homework that will be due on Monday. And then next week, we're going to start with chapter 10. We're going to start talking about parametric curves and polar coordinates. We'll do that for our last 2 weeks. I'll let the homework that I open next Monday be open all the way to the end of class. December 4th is our last day of class. This is when you will have exam 3. Exam 3 will be in class on December 4th. And then your final exam, let me pull up your syllabus. You guys are section 002. Your final exam is December 9th at 8 a.m. So please put this in your phone right now with an alarm. Everybody, put this in your phone right now with an alarm. It's not your normal time, and it's on a day that we don't have a regular class. During finals week, we won't have a regular class. Our last day of class is December 4th. So then the following Wednesday, you will have your final at 8 a.m. So everybody, please put this in your phone with like 2 or 3 alarms. An alarm that goes off at like 7, an alarm that goes off at 7:30, and maybe a notification the day before.
What days do we have class next week?
Monday and Wednesday.
Okay.
Yep. So the college is closed on Thursday for Thanksgiving, closed on Friday for Thanksgiving, but we will have class Wednesday and Monday. All right, everybody clear on where we're going? So I'll see you guys Friday, then Monday and Wednesday of next week. You'll have Thursday and Friday off. Monday and Wednesday of the following week will be regular class days, and then you have your exam on Friday. That's exam 3, your last midterm exam. Exam 3 will be Friday, December 4th. And then the final exam will be Wednesday, December 9th. And that's at 8 a.m. And that's going to be the end of the class, guys. So congratulations, you've made it through the roughest part of the roughest course in the calc sequence. Take a deep breath. Please review all the notes and comments I've left on your exams and study guides. Those took quite a while to write, and you want that information to be incorporated in your brain for the final. That's it. You guys have a lovely rest of your day, and I will see you next time.
Thank you, Professor. Have a good day.
You too.